to this episode of Kennedy Saves the World. And today we are going to venture into the world of physics, which is exciting and dynamic. And there are warring factions. And it's got a very dramatic history that leads us to where we are right now, which is a very, very exciting place, because now we are using technology to gaze back billions of years, 13 billions of years, to the origin of the universe, when things began and things quickly fell apart. And the story of physics, according to my next guest, is really about putting that world back together from when the universe began. And it's sort of a process, it appears, of reverse engineering. And it's fascinating. And sometimes it takes a while to read parts of his books because he's really smart, but he lays it down for the laity. And that means you and me can enjoy Michio Kaku, the incredible, legendary theoretical physicist who is the co-founder of string field theory. He has a brand new book. It is now on the New York Times bestseller list. It is called The God Equation, The Quest for a Theory of Everything. Welcome to Kennedy Saves the World, Dr. Kaku.
Glad to be on this show.
So I really like your book because I get the sense that you're really passionate about the history of science. And there you have a wonderful way of revealing these stories about physicists that make them sort of gooey and dramatic and interesting, and things about their lives that you don't normally hear about in a high school or college physics class. But for those who did take physics, like I did, and who did enjoy it, like I did, learning more and more about the stuff where we first laid our foundation is so satisfying, and your book does a great job of that. Now, when I say that we have to go back to the Big Bang, a big part of your book and a big part of the history within the book is the history of how we discovered the four forces and how that changed not only physics and science, but how technology sort of followed from that. And you write that when the Big Bang happened, there was perfect symmetry and there was only one force. When did that symmetry fall apart?
Yes, right after the instant of the Big Bang itself, the superforce at the beginning of time began to crack. And they began to split off to give you the four forces that we have today: gravity, the electromagnetic force, which lights up our cities, and the two nuclear forces. And each time we unraveled one of those forces, world history changed. When Newton wrote down mechanics and law of gravity, that gave us eventually the steam engine. They gave us machines, dynamos. The mechanical age is a direct product of Newton's theory of mechanics. And then Maxwell and Faraday worked out electricity and magnetism, and that lit up our cities with dynamos and electricity and vacuum cleaners and refrigerators. And then when Einstein wrote down E equals mc squared, that unraveled the secret of the stars, where M, which is the mass of a star, turns into E, sunlight, the energy of the star. And now we're embarking upon a theory of everything. The whole shooting match into an equation perhaps no more than 1 inch long. Einstein spent 30 years chasing after it, and he missed. But today we think we're closing in on it. And that's what's so exciting, closing in on the equation that set off Genesis, that set off the beginning of the universe itself. That is so exciting.
So what do we have to know about the exact moment of the Big Bang that will further inform in order to allow physicists to codify that unified theory?
Well, we think that at the beginning of time, the universe was in perfect symmetry. All the four forces were unified as one superforce, but there was a crack. For some reason, there was a crack in the original Big Bang, and the universe began to explode into the four fundamental forces that we have today. So in some sense, as you pointed out, we're going backwards. We're going backwards trying to figure this out. Now, I first heard about this when I was 8 years old. When I was 8 years old, everyone was talking about a scientist who just died, who couldn't finish his greatest work. They put a picture of his desk in the evening news showing the book he couldn't finish. Well, I was hooked. I had to know what was in that book. Why couldn't he finish it? He could ask his mother, right? Well, I went to the library and I found out it was Albert Einstein who wrote that book, and he couldn't finish it. The theory of everything, an equation perhaps no more than 1 inch long that would allow us to, quote, read the mind of God. Well, I was hooked. I had to learn everything about that equation. And today we think we have a candidate for the theory of everything. In fact, just 2 weeks ago, you heard the news outside Chicago at Fermi Laboratories. We found a crack in what is called the Standard Model, which more or less describes the particles that we see today. But that can't be the final theory. The Standard Model is rather ugly. It's very clumsy. And we think there's a higher theory, a beautiful theory, a theory that perhaps is no more than 1 inch long. And I tell people that are listening to this radio show that if you ever find this 1 inch equation, be sure to tell me first. And we can split the Nobel Prize money, you and me.
That is fantastic. And it's interesting because, you really, you go through the different physicists at different times who sort of pulled things apart and thought about them differently, including, Paul Dirac and the Dutch grad student who, with his advisor shared the Nobel Prize. And throughout the book, there are these great stories of non-traditional thinkers. And that's something that I like to take in my own life and my own work is, it's obviously I'm not going to do vector calculus or theoretical physics when I work, but I am able to, as everyone is, come upon problems and conundrums and try and take them apart and look at them in a different way. And that's really satisfying. And even when you write about Einstein, when you talk about someone, it's now just a cultural, it's part of our lexicon that if someone's really smart, it's like, oh, he's a real Einstein, who's the smartest person that most people can think of. But what I didn't know until I read your book was that he was actually, he came in conflict with his professors because he was so smart and he knew that his intelligence was beyond theirs, and he didn't get good recommendations from his professors. And so he was almost broke and done for before his physics career really began.
That's right. In fact, he even had a job as a salesman, trying to sell, for example, life insurance. Can you imagine opening the door one day and there's Albert Einstein trying to sell you life insurance? Well, we have this image of physicists watching the CBS program, The Big Bang Theory. Sheldon works on string theory. That's what he works on. But we physicists are not all like Sheldon, okay? We're normal people.
Yes, and with very interesting brains. And, there are different sides of physics. And as I'm reading this book, I'm wondering because, obviously Einstein had his own issues with quantum theory. And there was something in his lifetime that was irreconcilable between quantum theory and general relativity. And you write that has dogged physicists ever since.
That's right. All of biology can be rewritten in the language of chemistry. All of chemistry can be rewritten in the language of physics. All of physics can be rewritten in terms of two theories. One is relativity, the theory of the very big, black holes, big bangs, quasars, galaxies, and the theory of the very small, the quantum theory, the theory that makes lasers and transistors, computers. This conversation is made possible because of the quantum theory. So why should God have a left hand and a right hand that don't talk to each other? These two theories are incompatible. They don't like each other. They're based on different mathematics, different principles. So what we want is a unified theory that can unite the very big with the very small. That is, unite black holes and big bangs with protons and electrons and mu mesons. That's the goal. And today we think we have it. We have something called string theory, which says that if we have a super microscope and could look at an electron, it's not a dot particle at all. It's actually a rubber band. And the rubber band vibrates in different frequencies. One frequency we call an electron. another frequency we call a neutrino. They look like point particles, but they're different vibrations of the same rubber band. So physics is nothing but the harmonies you can write on these vibrating strings. Chemistry is the melodies you can play when these strings bump into each other. Mm-hmm. The universe is a symphony of strings. And then the mind of God that Albert Einstein wrote about for 30 years of his life, the mind of God is cosmic music resonating through hyperspace. We even have a candidate now for the theory of everything.
And what is that?
Well, it's called string theory, and I'm proud to say that I'm one of the pioneers in the subject. It's not quite in its final form yet. Now we realize that in addition to vibrating strings, we have vibrating membranes. But we think this is it. And we think that it makes a correction to Einstein's theory. Einstein said the universe is a bubble. We live on the skin of the bubble, and the bubble's expanding. That's called the Big Bang Theory. String theory says there are other universes out there, other bubbles. There's a bubble bath of these universes. And when these bubbles collide, or these bubbles fission, that's the Big Bang. And then the next question that everyone asks me is Elvis Presley still alive in another parallel universe? Well, yeah, according to the quantum theory, there's a certain probability that Elvis Presley is belting out hits, but not in our universe, in another universe. Sorry about that.
So what about the theory that, we are living in a computer simulation? Could that just be another manifestation in a different universe? And if so, when do we get control of the joystick?
Well, the question is, how do we go between universes? Well, there's a catch. There's always a catch someplace. According to quantum mechanics, everything vibrates. These are vibrating strings, music, basically. That is the nature of matter itself. But you see, we don't vibrate at the same frequency as these other universes. We have split apart. And therefore, don't believe that you can one day suddenly hop across universes. Now, in the PhD program at my college, we give a homework problem. Calculate the probability that you will wake up tomorrow in a parallel universe or wake up on Mars tomorrow. It's a very small number. It's longer than the lifetime of the universe. In other words, you're going to have to wait an awful long time to meet Elvis Presley. So he could be belting songs out in another universe, but it's not for us. He's not vibrating in our frequency anymore. Sorry about that.
We have more of this interview in moments coming up. You talk about, your book is called The God Equation, and you talk about, Einstein's vision of the mind of God, and you do talk about God. Are you a theist, and is that important to your work? How much of that is a driver to the questions you try and answer?
Well, Galileo, I think, said it best. The purpose of science is to determine how the heavens go. The purpose of religion is to determine how to go to heaven. So in other words, science is about natural law. It's about the laws that govern the universe, while religion concentrates on ethics, how to become a good person, how to go to heaven, and they're compatible. I don't see any incompatibility. Now, Einstein did not think that there was a personal God that answers your prayers, smites the Philistines, gives you that bicycle for Christmas that you've always wanted. He didn't believe that. He believed in the God of order, simplicity, beauty, elegance. The universe is gorgeous. And it didn't have to be that way. The universe could have been chaotic, ugly, random. It could have consisted of a mist of subatomic particles with no intelligence in it. But here we are, contemplating these questions in a universe that is blindingly gorgeous. So Einstein didn't think it was an accident. He thought of the universe as a library. A gigantic library, and all we could do is just take the first book, read the first paragraph, and figure out what the first paragraph means. But in front of us was this ocean of knowledge in this library, which could not have been just an accident.
It's really interesting because when I studied quantum mechanics at UCLA, it wasn't through the physics department, it was through philosophy. And there were a lot of questions that physicists deferred to philosophers in terms of quantum theory. Is that interesting to you? And what are the ones that are most interesting?
Yeah, well, when you get right down to it, quantum mechanics is the most revolutionary theory known to science. We think that an electron can only be one place at one time, right? That's just common sense. How can an electron be two places at the same time? But that's why we have lasers. That's why we have transistors. That's why we have this conversation by satellite. All this technology is made possible because electrons can indeed be two places at the same time. Now, why? How is that possible? Einstein tried to wrap his head around it and could not. We just simply get used to it. We just get used to the fact that electrons can be multiple places at the same time. And that's how we make transistors. That's how we make electronics. That's how we make the internet. However, there is another theory that says that, well, the electron splits into two universes. Just like I mentioned, if you apply that to the universe, then the universe is a bubble which can split. And that means that big bangs could be taking place all the time. Someplace far, far away, another universe is being born so far that we can't notice it, but it happens in the same way that electrons can be two places at the same time. Now, some people say, well, I can't visualize it. My attitude is, get used to it. It's just the way the universe is. The universe is a lot stranger than we originally thought.
And physicists are always seeking symmetry. As you pointed out, you quote in your book, to a physicist, beauty is symmetry. What happens when you're seeking that kind of symmetry and you know you're so close? And at the end of years and years of work and research and mathematics, you come up with an answer that is either anomalous or infinite. What is that feeling like?
Yes. In other words, many people have tried. The greatest minds of the human race, going back to the Greeks 2,000 years ago, the greatest minds have tried their crack at a theory of everything. But every time they try something, it turns out to be either anomalous, that is, 2 + 2 = 5, that is, it's not self-consistent mathematically, or it blows up in your face. The only theory which works is string theory, because string theory says that relativity and the quantum theory can be summarized in the lowest octave of a vibrating string. This means there could be higher octaves, and we think evidence of that may have been found 2 weeks ago at Fermilab outside Chicago. They found that the muon, a subatomic particle, has different subatomic properties than the electron, meaning that there could be another particle out there. These particles could be higher vibrations of the string, the next octave. We are the lowest octave of the string, according to this theory, which has not yet been proven. But there are higher octaves out there. So this music that pervades the universe could have the first evidence for it could have taken place just 2 weeks ago.
And why is it necessary to have a unified theory? Is it just that everybody who has followed Einstein wants to finish his work? Why is it so maddening for physicists to leave that undone? Is it because you feel like you're really close? Or is it just some sort of summit fever that is inexplicable?
Well, first of all, we have many questions that cannot be answered using Einstein's theory of gravity. We cannot answer what happened before the Big Bang. What is the universe expanding into? Is there a white hole at the other end of a black hole? Are there other gateways between universes? None of these questions can be answered using Einstein's theory. Einstein's theory blows up at the instant of the Big Bang and the center of a black hole. The theory is useless. That's why we need a theory of everything. Children ask the question, what happened before the Big Bang? What is the universe expanding into? String theory can answer this question. In other words, string theory says that there could be bubbles out there that collide. Each collision of a bubble universe creates another universe, and that's the Big Bang. And what is the universe expanding into? Well, if you have a bubble, its two-dimensional surface expands in the third dimension. So if our universe is four-dimensional, it means our universe is expanding in a higher dimension. Now, this means that there is a multiverse of universes, and these are all testable ideas. We hope to launch a satellite called LISA, Laser Interferometry Space Antenna, which will give us baby pictures of the instant of creation. It's a gravity wave detector in outer space, funded by the European Space Agency and NASA. And we hope to get vibrations from the instant of the Big Bang and then create a baby picture of creation itself. And then maybe we'll have evidence of the infant universe emerging from the womb. And then maybe evidence of an umbilical cord connecting our baby universe to a parent universe. All these questions cannot be resolved using Einstein's theory. We need a theory of everything to answer the question, why are we here?
So when did it occur to you to marry string theory? And I'm curious how long that had been around when you were doing your research with Faraday and Maxwell's field theory.
Well, believe it or not, string theory goes back to Pythagoras, the Greek mathematician of 2,000 years ago.
I'm a fan.
Yeah, Pythagoras noticed the lyre string and he plucked it, and the longer the string, the lower the note. He went to a blacksmith shop and found that the longer the rod or sword, the lower the vibration. And then he said, aha, I can use mathematics, the mathematics of vibrating strings, to explain music. And that's right. The man who figured out the laws of music was Pythagoras, using the mathematics of vibrating strings. Well, today, of course, we don't have vibrating strings that you can pluck. We have infinitesimal little strings that when they vibrate create the electron, the proton, the neutron. They're nothing but different musical notes. Now, the modern version of string theory was found by accident in 1968. Two postdocs were just flipping through a math book and stumbled on the Euler beta function, a beautiful mathematical function that seemed to describe the interaction of pi mesons. Now, science is not supposed to be like that. Every textbook says you have to experiment, hypothesize, experiment again. These guys stumbled on it by accident. In other words, we were not supposed to see this theory in this century. It's so advanced. The mathematics have bowled over the mathematicians, opened up new areas of mathematics. If you want to win the Nobel Prize in Mathematics, the Fields Medal, you have to know string theory, because that's where a lot of the new ideas are coming from. This theory is smarter than we are. We were not supposed to see it, but we have by accident. Thank goodness we discovered it by accident.
And now you cannot unsee it. So last question, what is your favorite particle?
Well, my favorite particle is the electron because it's a light particle, very easy to move around, and that's called electricity. So electricity is nothing but the motion of electrons that give us the electric revolution. Everything you see around you is energized by electricity. And why? Because the electron is a light particle. It doesn't interact that heavily with other particles. The nuclear force does. So the nuclear force is a lot harder to solve. But electricity simply dances at the end of a wire because it is lightweight and its coupling constant is very small. And thank goodness, if the electron were like the nuclear force, none of the electric revolution would have been possible. We'd be back in the dark ages. So thank goodness the electron is light and is lightly coupled.
Dr. Michio Kaku, his book, The God Equation, The Quest for a Theory of Everything, now a New York Times bestseller. Always something to think about. Keep illuminating us. You are our personal electron. So much possibility, so much mystery, but so satisfying. Thanks again, Dr. Kaku.
My pleasure. Anytime.